thanks everybody. Another episode of Shop Talk. Thanks for joining me. I also want to say a big thanks to my support team here. I've got the Cluffy people in the background. My wife's here helping me. Belated Mother's Day to all the mothers out there. But yeah, it takes a lot of people to pull this together, and I appreciate everybody's help, especially doing this at night like this. So yeah, so what I'm trying to do is a little bit of a trying to keep this rolling in a kind of a little bit of a logical order here. I don't want to jump around too much. I know we talked about primary, secondary piping last week, and this week we're going to talk about hydraulic separation, which kind of is primary, secondary. So I'm going to review that a little bit for people that didn't tune in last week, so we don't get lost here a little bit in the shuffle, just kind of jumping topics a little bit. So we'll do just a quick housekeeping slide or two here, and then we'll roll on. Yeah, these are just some of the past and upcoming things that we'll be doing. There's a number there if you do break down. In fact, I was on a B&G webinar today that the presenter actually broke down and had to hang up and dial in again. So if that happens to you, where you lose your connection or it gets fuzzy or something weird, sometimes just hang up and dial in again or log in again if you're using your computer. And that's just a tech support phone number for the GoToMeeting people. If you have ongoing issues, sometimes they can sort that out and help you a little bit. Yeah, and thanks again to Mechanical Hub for sponsoring this, and this was kind of their idea to put all this together. So I know some of those folks are online with us here today in the background, so they're going to be watching questions. And if you want to raise your hand and ask a question as we're going along, Mary's going to watch for hands raised in, and Kevin and the other folks are going to watch for any typed in questions. And Kevin helps me a lot where he'll answer some of the questions. He'll just type in a response if it's something that he can handle as we're going here. But I told him I don't mind people interrupting me with a question if it's something that I'm on the slide. And my wife said it forces me to take a breath and not talk so fast too. So yeah, just whatever you have as we're going through this, shout it out or raise your hand if you want us to open your mic and we can chat a little bit. So hey, we've been doing great with the donations, and a big thanks and a big shout out to all you folks for helping us. Last week we $480 for the Meals on Wheels, which Cluffy was generous enough to match on that. So a big thanks for that. And we're going to try and do that on every one, have some kind of little charity that we can link in with just to help somebody out. And so I chose the one for this week, and it's one of my favorite charities that we help a lot with our local chapter here, and also on the national level. We're big dog fans, and we've always got at least 2 rescue dogs in the household here. So we'd ask you to either donate to the American Society on the national level. They make it really easy at their website. Just click on it, and the sky's the limit for what you want to donate there. But if you would prefer to do something, for your local shelter, take a bag of dog food to them, they appreciate that sometimes. So that's what we're thinking for tonight's, and we'll and Ellen and I will match the donations too. So all right.
I'm in.
All right, she's in. So resources, a lot of the slides that you're going to see tonight come out of some of the hydronics issues. These are a technical journal that Cluffy publishes twice a year. John Siegenthaler does the heavy lifting on those. A big shout out to John for making these so interesting and so fun. So if you aren't getting these, you can go to our website there at cluffy.com and sign up. They're free. We mail them to you and we publish them. We can get you back issues if you like the hard copies. They're also on our website as a PDF. So if there's something you see as we go through here tonight, these slides, by the way, we'll share with you if you want them. Let us know and we'll send you probably a PDF of them. But if there's something, a drawing or something you want to use, you can certainly go to some of the back issues and find a lot of really great information. And we try and keep them fresh. That's why we keep doing these instead of just letting it sit out there. We every 6 months we'll come out with another issue. We're going to be talking about air-to-water heat pumps. We think that's kind of an emerging technology as more and more cities and states are looking at going fossil-free. We're thinking, well, how are we going to play as a hydronics company or industry if the gas and oil goes away? So we're thinking that might be a good topic and be interesting. So the other thing one last thing I'll say on this is if you have something on your mind, a topic you think we should be talking about in the industry, let us know, because we're always looking for topics. We try and plan these, a couple issues ahead. So we're always looking for new ideas or something that you think might be of interest to all of us, to the group, to the industry. So let us know and we'll put that on our list. So separation. So these are the t-shirts, by the way, that Sharon at our company developed, and these are going to be the prizes for the trivia contest. So in fact, why don't I just give you that right now since I'm on this slide. So I'm going to need to know the the name of the song and the artist on this one. And this one kind of, I thought fit, I heard it today, and it kind of made me think of being shut in here for the last month. So here's the lyric. With the birds, I'll share this lonely view. If I could sing it, you'd recognize it right away. Let me repeat it. With the birds, I'll share this lonely view. So
I know it.
no, you can't play. So, and Mac, you can't play either.
So. I know it too. Can I guess?
No, John, you can't guess either. So, all right, type it in if you think you know, and we'll get a T-shirt coming your way. We got to send one to New Zealand for the last winter, so we're just getting them. We got an on-demand company that does that for us, so we'll get it out to you. All right, so back in the day, some of you folks online might remember these days, some of these boilers of years gone by, the glow core up there on the upper right, the little MZ monitor there in the center, and of course, we're still using the heat exchangers like you see on the lower left. And common to all these is they're a pretty high pressure drop type of heat exchanger in this boiler, so they take a bunch of pumping power to make sure that, in fact, the table on the glow core over here, you can see how much pump and what kind of pressure drop there was through that boiler. You can see the different sizes and the flow rates and the pressure drop through that boiler. And so what we didn't pay attention to, a lot of us, myself included, is that we had to really be sure that when we sized the circulator for this application, for this boiler and whatever distribution piping and emitters that you're going to tie onto it, that you had enough pumping power to cover all that. Rethinking that, if we would have been paying a little bit more attention to primary, secondary piping and hydraulic separators, which is what we're going to talk about tonight, these boilers probably would have done a lot better than they originally did, where people were just trying to treat them like we do a cast iron boiler, which has virtually zero pressure drop going through it. Because of the wide open sections, we were trying to pipe these boilers that may be a replacement, took out a cast iron boiler, put one of these in, left the same pump there, thought we could get away with it, and we got rewarded with what you see in this picture over here on the left, heat exchangers that would burn through. They would overheat, they would pop, they would bang, they would flash to steam, and eventually, like, and you can see in this picture, there's actually a couple pinholes squirting water up in the center of those, where those tubes are burned black. So, and really, even some of the copper tube boilers could have done a lot better with primary, secondary piping or hydraulic separators, because they had a bit of pressure drop that you had to make sure that you had covered. So that kind of takes us into primary, secondary. And so let's put some numbers to a high pressure drop type of boiler. And this comes right out of one of the hydronics issues. So if you look at, pay attention to, hopefully you can see these clear on your screen, all the different pressures that that we have going on in this picture here as we start pumping through this this boiler with a single pump. And so we've got a high pressure drop boiler here, call it a Munchkin, whatever brand you'd like to use for that type of boiler. We got a circulator pump. We also put in a high pressure drop distribution circuit on that, the red circuit. So if you look at all the pressures here, notice here's our point of no pressure change. So we've pumped this thing up to a 12-pound static fill pressure. And now we're going to switch on this high head circulator. And you'll see that we immediately are adding 10 pounds of pressure differential across that circulator. So now we've gone from the 12 pounds, 22 pounds at the discharge gauge on that. Go around through the circuit here. Obviously, as we go through the piping and the fittings and the heat emitters and everything else, we're going to scrub away or use up some of that delta P that the circulator is imparted to that circuit. So we're getting around here and we come back, we get down to the end of the road here, and we drop down to 17 PSI. So we went from this 22 at the discharge through the heat emitters, through the circuit, down to 17 PSI. Now, this smaller circulator on a smaller distribution over here is off right now. So if you pay attention to what's happening, I've got this 17 PSI here right now, which means I've got 17 PSI here. I've got 17 PSI going around the loop, and I've got 17 PSI against this check valve in the discharge side of that circulator. So that I'm backseating that check valve with that delta P that's being developed by this big pump. Now let's take a look at a pump that might be on a circuit like that, and let's go over here and look at that little circulator, look at the pump curve here. And notice the circulator at this low flow, no flow condition can only develop about 4 pounds of pressure differential. And I've got 5 pounds here. So that circulator is never going to be able to pop open its check against the pressure that's against it here and be able to flow through that circuit there. So therein lies the problem with if you do come up with a pump that can overcome your pressure drop in your boiler, in your circuit, and you have smaller pumps on that same boiler on that same distribution, you can see where you've got the problem with the high head. It's actually overpowering the small circulator there, and you're never going to get flow through that. Now, if the the bigger one shut off, you'll get some flow through that, but you might not have enough that you're going to overcome the pressure drop in this and get enough flow through that boiler that you don't start kicking it out on high limit, overheating that, and eventually you could end up with what I just showed on that previous picture, where you're going to overheat the heat exchanger in that boiler. You're not scrubbing that heat out of that heat exchanger with not enough flow going through it. So that's what we're going to get to with this primary secondary, where all these issues go away. So we talked about this, I know, on the last one, but let's just review it a little bit for those that are just tuning in. So the concept, came out of the Bell and Gossett folks, and they said, you know what, if you put a couple T's together and you put them close enough, and you had this pipe here size, let's call this the primary loop, large enough to accommodate the flow going through this loop through the boiler, and these T's are close enough together, very little pressure drop when you have two T's closely spaced like that. So now what I can do is I can just connect whatever size circulator I need to overcome whatever load, whatever pressure drop is in this secondary circuit. So now this could be still a high head boiler with a high head pump here, and this could be a low head, this could be a high head here. And by putting this little separation, this closely spaced T's with the zero pressure drop between them, I isolate, hydraulically speaking, I isolate these pumps from one another. Now, obviously they're all in the same water. Some people say, well, is that a heat exchanger in there? Do you have two different fluids going on here? No, there's nothing inside there. It's just the space between there that's creating this separation, this low pressure drop separation device, which we call closely spaced T's, and that's what makes it primary secondary. So if you walk into a job and somebody tells you, oh yeah, I piped it out primary secondary, and you look around the room and you don't see two T's close together within a couple inches of one another with a pump on one side pumping out of those T's coming back in the other side, it's not a primary secondary. If this pipe was connected down here on the return, it's no longer primary secondary. So it has to be those T's closely spaced together. So it was fairly understandable once you understood what was happening between there. And this is where it really helped us a lot. We said, okay, let's take the boiler out of this loop now, like we have over here, call that a cast iron boiler, low pressure drop. We can flow through that pretty easily. This boiler needs to have a circulator dedicated to it to overcome that pressure drop. Well, by tying it into the loop with these closely spaced T's, now we can size that appropriately. Now, the other thing that came up, and Dan helped me out with this, Holohan, I said, now, which is the primary and which is the secondary? This seems to be confused in a lot of people's mind. I always thought, well, if it's the boiler, it's the primary. It's the hotter, that's the primary. And Dan said, well, Gil intended it to be wherever you connect the expansion tank develops the primary loop. So in this case, with the expansion tank connected in here, that becomes a primary loop, even though a lot of people say, well, no, it's always the loop with the boiler. And well, from my understanding, it's the expansion tank connection that establishes that. Now, that being said, this circulator is pumping away from this point of no pressure change by this section of piping right here. So it does see this as a pumping away on both these circulators, pumping away here into the boiler, which gives me that extra delta P in my my high pressure drop type of heat exchanger. And this circulator is also pumping away from the point of no pressure change. So then, we talked about this a little bit last week, that, the downside with this series primary loop is every one of these is going to see a lower and lower temperature when they're all running. Let's say I'm coming in here at 160, coming back at 140, blending with that. You can see how the color of these lines changes as we go around the loop here. I see a lower temperature, lower temperature. So you had to know that. So if you need the same temperature at the end of the road here, with this series primary loop, you're not going to get that. Think of it's kind of like the old Christmas tree bulbs. When you pull the first one in series out, the rest of them go out because you're broken in the series. That's kind of one of the downsides of doing the series primary loop. So about this time, and I would say this is going back maybe 15 years, is when we started hearing about this thing called a hydraulic separator, or low loss header was another word for it, hydrosep, different names for it. And so I got introduced to this when I started working with Calefi, and I think we're kind of one of the pioneers here in the US with this type of device. And if you look at it, if I took a set of closely spaced T's, let's take two sets of them, if I smushed them together and put a chamber in the center there, I've actually built this device over here, which is called a hydraulic separator. And if you look at it, there's my closely spaced T, so I could have my boiler connected over here with its required circulator on it, circulate through there. And then over here on the distribution side, I could have a circulator, I could have multiple circulators, I could have a circulator with zone valves, I could have different size circulators. And this little chamber, I say little, I'll show you the size of that in a minute. This chamber in the center is what establishes that disconnect, that hydraulic separation that we're getting between these closely spaced T's and this common pipe here. I've now established in this device here.
Hey, Bob.
Yeah, go ahead.
Sorry to interrupt. I didn't want you to get too far away from that last slide. You had a figure 5.7 and the one just before this. And Bill is asking in that figure 5.7, if you were to do a system like that, I'm assuming you would put the expansion tank before the pump, or would you pipe it off the boiler if that was possible? Or is there somewhere else you would put it?
Yeah, in this basic, what I consider this is the boiler is within the primary loop. So I would probably put the air purger right here. In fact, I'd probably have an air separator there, and that would be one of the cases where you might put the air separator and the expansion tank in one package right there. So then this circulator is pumping away from it, and through this piping here, these circulators will also pipe away for it. So you establish your point of no pressure change. I should probably put that in there, but I was trying to keep the drawing just simple to show the closely spaced T's. But that's a great question, and you'll see more of that as we go through the drawings. I'm going to show you some options for where expansion tanks can tie into a system. In fact, we're going to do next week, we're going to do an expansion tank specific webinar. I'm going to show you a lot of different options for type of tanks and also where they can go in. But yeah,
thanks, Bob. Yeah, that was from Bill D'Agostino. So.
Yeah, thanks, Bill. Any others while we're at a good point here? That
well, Bob, it doesn't have to do with separation, but would you accept a duel or two people winning a t-shirt? Because we had two people the answers just flew in all at once. But Kevin Rafferty and Bill Jerome are both saying that it was Red Hot Chili Peppers Scar Tissue.
That's exactly right. That was quick. I thought I was getting a little tougher ones here. I thought maybe if I changed the genre a little bit, made it a little more recent of a song, I might make it a little bit harder. So I'll try harder next time to get a tough one. But thanks for playing, and you're right. And we'll need your size and obviously a mailing address to get those shipped out to you.
Okay, thank you.
All right, thanks. So getting back to this, so we said, okay, I think we're onto something here. We've got a better mousetrap. We can make it simpler for the installer. He doesn't have to assemble this on the job. If this is sized properly, it's going to work. There's nothing you could do with the pumping on either side of this if this is sized properly for the flow rate, and we'll get to that in a minute, that you won't have hydraulic separation. And by the way, couldn't we put an air vent on top of this? Because this is going to be a low velocity zone, this big wide spot in the road, let's call it. It's going to turn into a low velocity zone. Great place for air to rise up and grab air. And couldn't we also catch some sediment at the bottom as the particles from a rusty old system come in here with low velocity going through them, they could drop to the bottom. So now I've taken my hydraulic separation and kind of enhanced it, turned it into air separation, turned it into a bit of a dirt removal function also. I could do other things. I could put a port in here that I could put a sensor in there. Some of the installers will take and put a rear mount gauge in there, a TMP gauge, so they can monitor pressure, temperature in the system. We make a sensor well that could go in there if you want to put one of the boiler sensor into that, where you can regulate your boiler condition from the hydro separator. We made that convenience port. And we'll talk about some of the other options, but I want to talk about how these are built and the importance of the sizing on this, because I've seen some out there that were kind of an attempt at this, but I know they're not going to work right because they didn't have these dimensions properly. And so let's just put some numbers to it and make an example of this one over here. Let's say I've got a 40 gallon a minute flow rate is my requirement. So I'm going to need a 2-inch pipe size on that. If you look up the chart, you'll see it takes about 2-inch pipe size to move 40 gallons a minute at about a 4 feet per second velocity. So the key to this is this chamber, the center portion here, let's call this the separator function here, needs to be about 3 times the diameter of the pipe coming into it. So if you decide that you need 40 gallons a minute and you need a 2-inch pipe, then this barrel needs to be about 6 inches in diameter. And if you do that 3-to-1 relationship, that's going to assure that you have enough get my pointer back, space in there, so to speak, that we're going to have a very low, look at the flow velocity from the top to the bottom of that with 40 gallons a minute going through here. I've got less than a half a feet per second velocity. So I've got very little movement from the top to the bottom here when I'm flowing that kind of rate, because I've just increased the size of that chamber by 3 times. I went to a 6-inch pipe with 40 gallons a minute going through it. That's where I get my velocity drop. Now, the other thing that's critical is the spacing between the tees, and here we just put some numbers to all this. So again, if you know the size of the pipe based on the flow rate that you want to run through it, then all these dimensions you can just calculate them, because you could make your own. And I'll show you some examples of some homemade ones here, but I've seen ones where they've taken that 2-inch pipe coming into it and they used a 2.5-inch pipe for the center barrel. You're not going to have enough space in there to get that separation. Basically what's going to happen when one circulator is running, it's going to induce flow on the other side, vice versa, depending on which one's running. You don't have separation because you didn't put enough space, enough room, a big enough space in the road, so to speak, to establish that separation. And you can kind of see what's happening here with the dirt particles as they come in there. Low velocity going on in here. Those particles can drop out. The same thing with the air removal at the top here. Now you can make it without either of these little functions in here. We've over the years enhanced the Cluffy version. First we put just a little perforated mesh in here to kind of stop some of the micro bubbles and get them to go up, and we've enhanced this even more. I'll show you as we go along here. So there it is. I mean, if you want to weld up one out of some pipe, if you want to make one out of copper and T-drill the side of it, whatever you want to do, there's the magic number. Now that does go, there is a little bit of engineering formula that we use, and at some point when you get into 12 and 14-inch pipe sizes, that math, we calculate it because you don't always find a pipe size exactly what you need. So we can kind of, go between the lines a little bit. There is some math involved in sizing it exactly right, but that's the basic rule of thumb is a 3-to-1 relationship will assure that you got plenty of space to make that separation work. So just moving along with this, as we progress with this, we came up with even better ideas to make this even, more user-friendly, give you more features, more functions in it. So we put a little bit better a media in the top here so we can get better air removal. We can get those tiny little micro bubbles that you see that when you churn up water, when you fill it for the first time, you've got that little cloudy water, which is entrained air and micro bubbles. So we put a little bit better air separation. And we did the same thing here at the bottom. We said, if we put a media in there, maybe we can get down to a 5-micron particle removal because they're going to collide. I call this a collision media. It's actually a coalescing media. Those little particles will collide as they come through there and drop out. Then most recently, we had a magnetic band on the bottom of this. So if you've got any tiny particles, even smaller than a 5-micron, which you'll see when we do the demo here at the end, this magnet will pull those out. So now I've got air separation, I've got dirt separation, I've got magnetic separation, and the first thing I wanted, I've got hydraulic separation by the size of the chamber and my closely spaced tees, so to speak, on the side of it. So there it is. That's what we ended up with it after 15 years of developing this product. We came up with what we think is an ideal device to do all this. So now one of 3 things is always going to happen when a separator is flowing. So if you look at the first one over here, think about this. If I've got a boiler, let's use that last example, and let's say I've got 40 gallons a minute flowing from my boiler through the hydro separator and back out to the boiler. I kick on my secondary, and if I happen to have that size at 40 gallons a minute, what's going to happen is the fluid's just going to go straight through this. It's not going to have any reason to go down and use the separation because I've got exactly 40 gallons coming in, exactly 40 gallons going out. That rarely happens. Maybe if you had a single pump boiler and a single pump snow melt or something like that, you could sheer luck, maybe get exactly 40 gallons a minute. So one of these other twos is going to be more common. Typically, this is what's going to happen. So you can see, obviously, if we've got 40 gallons per minute flow coming in this and only 30 gallon a minute demand on it, some of that flow is obviously going to go back down through the separator and back to the boiler, and you're going to get a blending of temperature here. Now, you might not want that because basically if I had a ModCon boiler over here, I'd like to have the coldest water coming back to it, but obviously if my flow rates aren't the same, I'm going to be blending up that return temperature. Let's say it's coming in here at, pick a number, 70 degrees, and blending some of the hot water with that 70, and I'm blending the return going back to it. It's the way it is when you mix 2 fluid streams at different temperatures and different flow rates, they're going to blend. There's really no way around that. Excuse me. And that could change. Let's say I'm doing some of the newer pumps that we have out now. Maybe I've got a variable speed pump over here, and that speed is going to change based on zone valves opening or thermostatic radiator valves opening and closing. So this flow can always be changing over here. It can be, modulate based on the pump speed or whatever it might be. That's changing the flow rate going out to my distribution. So then this number here is going to change based on what that mixing is. And we've got a formula for that. It's called the mixed temperature formula. You need the two temperatures, you need the flow rates, and you can calculate what this number would be if you put that into the formula. And if you know the flow rates and the temperature, I can predict what that's going to be. Now that's a reason that if you want to, we put a sensor well in here, but really if you want to put a sensor on that's going to modulate your boiler based on what's actually going out to your system, I'd like to see that sensor downstream about 6 inches. So I'm actually measuring the blended temperature. If I put that sensor in there, I'm going to measure the temperature right here, but that doesn't necessarily mean that's what's going to be going out to the distribution. So either put a well in there, strap on a sensor and insulate it well, and use that to tell the boiler what's going out to your distribution if you want to modulate your boiler temperature by what's actually going out to the load. And here's
Hey, Bob?
obviously the other, yeah.
Sorry to butt in here. Another question. Why do some manufacturers like Reisman make a low loss header that's square instead of round? Does that make a difference? And this is from Stefan.
Yeah, no, that's a great question. And yeah, in fact, we made a square one. We call it the Hydronic. I think we still offer that. I don't know why. It doesn't have to be square. It doesn't have to be round. It could be oval.
Do you think it's easier or less costly to manufacture a square one than a round one?
Well, I'll tell you, it's easier to weld a square tube because you can get everything nice and plumb and square when you put it on there. It's tricky to bore into a round tube and get everything plumb and perpendicular and all that. So it could have something to do with that. Usually they just use a piece of rectangular tubing that you buy off the steel rack. So it's a simple thing to make it. We make our vessels, again, specific to the size we need. So it might start out as a sheet of tube that we roll or sheet of plate that we roll to the dimension we have, and you'll see the belly weld on it or the seam weld on it when we do that. But yeah, no, it could be square. I know there's some other brands out there. I think Sinus uses, I don't say square, I think it's actually rectangular. Yeah, it could be either way. Like I say, there's certainly some advantages to when you're trying to fab and weld on a square as opposed to a round. You might be more limited on sizes you can get. If you are making it out of some off-the-shelf rectangular tubing, you're going to be limited by what you can buy. So that might be the downside of it. But you'll see
well, thanks,
the
Bob.
homemade ones here that people kind of colored outside the line as far as the shape. So anything else while we're in the question category there? Let me look up.
Stanley had a question here. It says 3 times the diameter of the boiler feed or the system feed.
No,
Am I right in thinking 3 times the largest diameter pipe?
Yeah, 3 times. So let's say this is 2 inch, then this needs to be 3 times that pipe size that's coming into. So this would need to be 6 inch. If this is a 1 inch, which is one of our more common sizes, then 3 inch would be plenty here. 3 times 1. If this was a 8 inch pipe coming in here, which we make, then you're getting pretty big. You're talking about a 32 inch diameter vessel to give you that 3-to-1 relationship. Now I will say on the bigger sizes that number does go off a little bit. You'll find if you buy our 14 inch hydro separator, 14 inch pipe size coming in, it isn't 3 times it. I don't know if Kevin, if you know that off the top of your head, but at some point we actually calculate the space in there and come up with it. But for the smaller sizes, I'm saying 1 inch, 1.25 inches, 1.5 inches, 2 inch, you're going to find that relationship is going to be about a 3-to-1. So 3 times the diameter for the center barrel as the pipe size that comes into it. And again, the pipe size going into it, you need to know what flow rate you're going to run through that to size that pipe. Once you know that, you could choose a pipe or a square tube or whatever to give you that that capacity inside of it.
Right. Thanks, Bob.
I guess it would be a little tricky with a square rectangular tube to come up with that size. You'd have to make sure that the space in there is big enough to accommodate the flow. So it'd take a little bit more of a calculation, I suspect. So again, getting to our last picture here. Now, obviously what we're showing here is if we've got more flow on this side than on this side, you can see where the temperature blending is going out here. That's where the blending point is now with this condition here. So you can see the different conditions, flow rate the same, less than, more than on one side or the other. And again, you want to know that because if you're expecting a certain output temperature to this, you got to make sure that the temperature coming in with the temperature returning and the flow rate going through it is going to give you that temperature. And that's why I like to put the sensor there. if I've got a boiler that can respond to an input for a certain temperature at once, and it sees this temperature is dropping from what my design or my demand is, what I'm trying to run out to my system, obviously you could fire up the boiler and you could get the output up to where you can modulate it up and make sure that you're getting to the load, the temperature you need to cover the load under the changing conditions in the building or whatever it might be. All right, so how do I size it? We've got separators from 1 to 12 inch in this example here. What you need to know is the flow rate. That's the larger the two. So let me just go back to a picture. It's probably going to be easier. So let's say I've got 40 gallons a minute here. I might have an application where I've only got a 30 gallon per minute load when I'm at design condition. Maybe I'm running a different delta T over here. You don't add the 40 gallon per minute that the boiler needs plus the 30 gallon per minute that the distribution needs and say, well, I need a 70 gallon a minute hydro separator. It's the larger of the two. So if this is 40, I'm going to go to my chart that I'll show you next and find a hydro separator that can handle 40 gallons per minute. And that could vary on either side. Let's say you've got a job where you've got a boiler over here that only needs 30 gallons per minute, and you've got a 40 gallon demand over here, because again, you're running a different delta T on that. It could be that either side could be bigger. It doesn't necessarily mean that the primary side needs to match the flow rate of the secondary side. So that's why we say pick the larger of the two. And we'll go back to this here. So let's say I've got a load, I'll pick a number, say 25 gallons per minute. I would just go and say, okay, 1.5 inches would give me the 25 gallon minute. Now we do have a little bit of wiggle room in these, and you can call us if you've got a job that says, I need 30 gallons a minute. Do I have to go up a size? Call tech support. They can give you, a little bit of a pass on that and say, okay, yeah, we can wiggle a little bit, because every time we engineer something, there's a little bit of a fudge factor built into it. And we find sometimes our competitor will be a number two bigger than us. And people say, well, your competitor can do it with a 2 inch. How come I got to go to a 2.5? Calliope, give us a call. We'll let you know what the a thumbs up or a thumbs down on that. And, when we talked about the pipe sizing here on the last couple webinars, we talked that typically a hydronic system, we're going to run between 2 and 4 feet per second flow velocity. That does change a little bit when you get into larger pipe size. In fact, the ASHRAE standard shows that when you size larger pipe, you go by the head loss per 100 feet of pipe. You don't use this velocity, and that velocity tends to get a little bit sometimes bigger in the larger pipe. So if you're trying to size, say, a 4 or 5 or 6 inch pipe, by this velocity number, you should really use this formula here to, and there's, as I Googled around, I found there's different opinions on what this number should be. But again, this is the ASHRAE, and if you put your faith and trust in the engineers at ASHRAE, that's probably the safe number to use. I bet there's a little bit of wiggle room in that also, knowing the way that they come up with those formulas. So am I clear, I guess, on the pipe, the sizing of a hydraulic separator, the larger flow rate, whatever side, if it's the primary side, secondary, it doesn't matter. The larger the two is what you size the size of the separator to. All right, so I'm going to clear up a couple things on this drawing. Somebody, good eyes, caught this last week. This is one of a design that Siggy did back in 05, and he had this one circulator after we just went through explaining the point of no pressure change and always pumping away from it. He said, it looks like that pump is pumping right at, and you're right, and that was a good catch. And Siggy said, you know what, let me clean it up. So here's a drawing that we're going to clean up two things. Is number one, we're going to change the pump so it's pumping away here from the point of no pressure change, pumping into that flat plate heat exchanger away from it. So I don't know if the person that caught that on the last one, thanks for pointing that out. And I'm going to show you even a better way of doing this, because this is obviously a pretty complex primary secondary, and this is a lot of work to put something like this together with all these T's and calculating all this pipe size and the flow rate from the boilers and the distribution, your indirect. What if we could clean this whole drawing up and make it simpler for you for sizing this? And so we're going to take that drawing there. I just kind of scrunched it up so you can't read as much on it. And now we're going to put a hydraulic separator in there. And look what we did to all the piping and all the labor that you'd have to do on this job. And also, we've taken out our air separator. We've put a dirt separator in that. I don't even know if there was a Y-string or any kind of separator in this one here. And I've also got a magnetic function. So if I'm going to use an ECM pump and I want to protect those pump motors from any fine metal particles getting into them, I've got a magnetic band. And I've really, cleaned up a lot of the piping on this. I've taken a lot of the complexity out of this. Just looking at the two drawings, you can see the difference. So I know you're going to say, well, it's going to cost, pick a number, $300, $400, $500, whatever the separator price might be. I can go to the wholesaler and buy a lot of T's for that kind of money. Well, yeah, you can, but you got to go back and put all that together. You got a lot of solder joints here, and I'm going to give you the air and dirt. Consider the air and dirt as a bonus. I'm going to save you money on your labor, and I'm going to throw in the air and dirt as a bonus for your separation by using the hydraulic separator. Now, do you need one on every single boiler that you put in from this day forward? No, you don't. I'm going to tell you that right now. If you're putting in cast iron boilers that have wide open passageways, really there's not a lot of value to add in the hydraulic separator. Yeah, you'll get your air and dirt magnetic function on it, but the boiler's going to be fine just pumping through it. Some of the new fire tube boilers under certain conditions can get away without it if you can assure whatever distribution flow rate that's going on there covers the flow rate that the boiler manufacturer wants through the boiler. Then you could do that, just direct pipe it right from the boiler to the load. You just got to look, they're trying to be clear when you give you information on the pressure drop. Usually they'll put charts in there and say, okay, if you use this pump, you got this much head available to do your distribution. If it's beyond that, they really want you to go back to either primary, secondary, or putting a hydraulic separator. We're pleased to see that. What am I doing for time here? More and more manufacturers are actually putting both drawings in their installation manuals. They'll show you primary, secondary is an acceptable way to do that. Hopefully they've got the expansion tank and everything in the right place in those drawings. Or they'll say, hydraulic separator is another option to make sure that we've protected the boiler. So here's some examples of some homemade. It's actually a fellow I met online on Heating Help, actually, that I gave him the information dimensions, and he's a welder. He does a lot of food processing welding. That's why it's all stainless. And you can tell some of these clamps, it's common in the food processing industry. And he said, well, can I make it out of stainless? Well, sure you can. What size does it need to be? I said, what are you flowing? So I gave him the information, and he actually made a right angle, I guess, version of it that went in a corner like this. So he came in once, and that'll work. They don't have to be directly across from another. And also some of the manufacturers will actually offset them a little bit when they come in here. That's fine too. But this works great. So there's his air elimination. I don't know that he put anything inside here when he built it. I never did see it as he was constructing it, but there's an example of you just use the math, use the formula that I gave him, and came up with the right size tube and the piping to build it out of stainless. And our friends, the folks at Aquatherm out there in Utah, this is one that they fabricated. A lot of connections on this. I'm not sure exactly what they're doing with all these ports, but I thought this was and I didn't get a chance to talk to him. I was going to call him before I got permission to use it, but I wanted to talk to him and say, well, what's going on with all the ports? And also it looks like it's a dual purpose hydro separator. He's got what, I don't know, 4-inch, whatever size this might be up here. Then you can see he's got some, I don't know, maybe call them 1-inch over here. So maybe he's got 2 different separation functions going on at once. I got to learn more about this, but it's just showing you again that you can see kind of the relationship on the size. Just eyeballing that, you can see that we've got the barrel, quite a bit bigger than the pipe size, not this hub necessarily, but the pipe size coming into it and the dimension of the barrel here. So yeah, I thought that's a pretty clever way of building one, and obviously that could be built to spec to the job. So here's one. This is actually what we do for our reps and some of our people that work for Clef. We make little cutaways of them. We just take them over a machine shop and they actually mill the face of it off here so you can show people what's inside there. So when we do a presentation or a demo or something like that, we can just, hand it to somebody. We can show them the magnet. We can show them the media in there. We can show them how it's built and stuff inside there. So when one of the people retired from Calefa here a couple of years ago, I turned one of them into a lamp and I put a plug in there. It's not UL listed, so I don't need any phone calls, but I just turned it into a lamp. There's actually USB charging connections in the center of this receptacle, so you can plug in something, your computer, something like that. You can plug in your phone to the USB ports, and you've got a lamp there. So maybe I'll do that for a retirement project someday. All right, any questions, anything going on out there? Hands raised or anything, Mary? It's like we got quite a few people on tonight.
Well, no hands raised, but Bob, I was just wondering if the person who saw that issue in that schematic, was that a T-shirt worthy find, do you think?
I think it would be. I think it should be.
I think so too. I think so
Yes,
too.
I
So,
don't know. I don't know. Is Siggy on tonight? I didn't look at the attendees list. He can give you a thumbs up or thumbs down.
oh,
We should
and
get one
it
to
looks like,
Siggy too, probably.
yep. Okay, and we just Benjamin Hicken, we do have a couple of hands raised, but this may have been from a little while. So, Benjamin, I'm going to unmute you. If you've got a question, speak now.
Shout it out.
Hey, Benjamin, are you there? Okay, I'm going to put your hand down, but hold on one more second, Bob. We've also got Anthony.
All right.
Anthony, I'm going to unmute you. You are now officially unmuted.
Hey.
Oh, listen, I raised my hand by mistake. I'm good. I'm sorry.
That's
Well,
all
it's
right.
good to hear you anyway. So,
Thanks, Bob.
Thanks. All right.
all
Well, let's
false alarms, Bob.
keep going. Or you got any questions or anything, Kevin? We'll keep rolling.
I'll keep going, Bob. I'm answering most of them
No, thanks.
here, but I'll butt in if I see something.
All right. So then the question becomes, after we had these out for a while, people said, well, where do I put my expansion tank? I've got all these different connections on this thing now. How do I establish my point of no pressure change if I've got, multiple pumps on the distribution? I've got a pump on my boiler. A couple things I want to show about these pictures. Number one, most of these high pressure drop type of heat exchangers, these little Geonomia heat exchangers, in fact, I got a little cutaway of one here. You can see a pretty small passageway in that heat exchanger. They're asking you to pump into the boiler. Now this, we kind of have come full circle on this. Back in the day when they would ship cast iron boilers, they were pumping in the return side. We were putting our expansion tank on the discharge side, and we started getting the trouble as we started putting higher head pumps on those systems, and now we're pumping at the point of no pressure change. So thanks to Dan Holohan, he kind of train the industry, and John and other people, pump away from the expansion tank. Either move your expansion tank, move the pump downstream of it, or move the expansion tank down to the suction side of the circulator if it's on the return. So finally we got people thinking pumping away, and now we come back to, well, now they want us to pump back into the boiler. Now what? What do I do with my expansion tank? So yeah, you do want to pump away from your expansion tank all the time. So here we're going to add the delta P of this little circulator when it's running. It's going to show up as a positive pressure in this restrictive type of heat exchanger. So there's a good place right there, pumping away. You say, well, what happens to the pumps that I start putting distribution pumps, maybe one, maybe two, maybe they're variable speed? Well, because this is that wide open, low velocity, low pressure drop zone, this point of no pressure change is established through this chamber, and whatever pump I would put up here on the outlet side, on the distribution side of the circulator, references this point right here as its point of no pressure change. So this becomes a point of no pressure change for this pump, whatever pumps I add on to it. So that's a good spot. It could be on this side. Really, any one of the four ports could be the expansion tank connection. I prefer one of these bottom two because, number one, it puts my expansion tank in a little bit cooler fluid. If I'm going out here at 180 degrees, obviously my tank up here would see 180 degrees on the diaphragm or the bladder, or the bag, whatever type of tank you're using. By putting it down on the bottom here, on one of the return sides here, I'm going to see a little bit lower temperature. Not a huge deal, but it might extend the life of that a little bit.
Ken was saying, why pump into the boiler? I think he's talking about this diagram here. And I always pump out of the boiler, he said. Ken Wilds, is that right?
Yep, that's an excellent question, and that's what we've been taught to do for all these years, is pump away from the expansion tank and out of the boiler. Here's the problem with these high pressure drop boilers. If you pump into the boiler, the delta P that this circulator can develop when it's spinning shows up as a positive pressure in here. So what happens on a lot of these little tight heat exchanger type of boilers, they have pressure switches on them. And if you don't maintain the pressure, usually about 8 PSI, I think is what those pressure switches are. If you don't have enough pressure going into that, you're going to lock out on that. And you know what? I'm going to show you that next week. You got to come back next week. On the back side of this display, I did a pumping away, and I'll show you what happens to an expansion tank when you pump at an expansion tank, and it's going to blow your mind what happens. So we want this circulator delta P, the pressure differential that establishes. I'll probably go back to that early drawing and show you that better, since I think we put the numbers on that. bear with me here for a second. I forgot exactly where it was. So see what happens when this is a high head circulator, and you see what happens here. If I'm starting with, let's say, a 12-pound static fill pressure, as soon as I kick on that circulator, we show it right here, that circulator is developing 10-pound pressure differential. So immediately I've got 22 pounds of pressure on the discharge side of that circulator. Now this drawing is showing you something different, not pumping into the boiler, but that's why we want that delta P that pump establishes. We want that to show up in our heat exchanger as a positive pressure to make sure that we don't drop down to where we lock out because of a low pressure condition in that boiler. I'll show you next week where I could actually pull a negative pressure inside that heat exchanger, that boiler. In fact, I don't know if I can spin it around quickly enough here. I actually put, give me a second here. A little teaser here. I'll turn my screen if you can see that. I've actually put that type of heat exchanger in my little expansion tank display that we're going to show, and there's a compound gauge up there that can go below zero, and I'll show you what happens when things go wrong with that type of setup. So yeah, it has more to do with expansion tank, and I don't want to confuse you too much on that, but we want to pump into these high pressure drop boilers. And if we're going to pump into the boiler, we've got to pump away from the expansion tank. And that's why it becomes more critical that we get that relationship proper, the expansion tank to the circulator. All right, so the last thing
Bob,
I
I
wanted
believe, I'm sorry,
Go ahead.
Bob, I think we've got a question from the audience,
Okay.
from Ken Wilds. Hold on one second here.
Okay.
Do-do-do-do. Okay, Ken, I'm going to unmute you. Hold on just a second. Okay, Ken, you are unmuted.
Can you hear me?
We can.
Okay, good. All right. I wasn't talking about pumping into the expansion tank, never was. This when you pump on the boiler, the temperature's at the highest temperature, lowest pressure, best opportunity to get the air out of it. So that's counterintuitive to me, and what I've been doing for 40 plus years.
Yeah, I don't know if everybody heard that, but that's a good point. And like I say, when we talk about expansion tanks next week, I want to go into that a little bit more because, yeah, I mean, it helps. Everything gets better when you pump away from the expansion tank. Your air removal, getting bubbles out of your system, you're making sure that your boiler's happy and everything. So there's a few different things that come into play when we have that expansion tank in the wrong place or the right place. But yeah, thanks for that.
But also where the water is the hottest is where you're going to get the most air out of it.
Yep. Yep.
Okay.
Exactly. So, and that's why, I think people misunderstand that, and they think the expansion tank always has to hang below the air purger. It doesn't. I always want my air purger, well, let me just show you here, at the hottest point in the system, because if this water's coming out here at, let's say, 180 degrees, that's where I'm going to get my best air removal. So I want my air purger on this position here, but I don't necessarily need my expansion tank, as you can see in this condition here. I don't need to have my expansion tank necessarily hanging off the bottom of the air purger, or air separator, whatever you're using. And I think people will misunderstand that relationship, that everything has to be grouped together. When you put an expansion tank, I've got to have my air purger. I do want my fill valve there for the point of no pressure change, but that's yeah, there's nothing better than pumping away to explain all this stuff. If everybody needs to have that in their library and read it as many times, it took me a few times to understand that concept of pumping away, but that's probably the best book out there for the graphic and the explanation of the expansion tank and pumping away.
Yeah, that's all I've ever done.
Thanks.
Thanks, Ken.
And so the problem over here is not the expansion tank location per se, but think about the dirt and any particles that come out of separation here, and they're going to come down and they're going to sit right on the diaphragm in the tank here. And so as that diaphragm moves, as the water heats and expands, now I've got the rust and the crap that's coming out of my system kind of abrading on that diaphragm. So all I'd want to do here is maybe put a T there and put an elbow and put a nipple and put my expansion tanks so it's not directly below where my dirt removal function comes off the bottom of that separator. That's why the X is through there. Hydraulically speaking, it's a great spot, but I don't want my particles laying inside my expansion tank there. All right. So think about this. So some of these boilers, in fact, this little boiler that I've been showing you right here holds a gallon of water, 1.2 gallons of water in that boiler. So that boiler can short cycle even on a low modulation rate if you've got a micro load on that. that boiler can short cycle. So if you think about this, by adding a hydraulic separator, I'm actually adding a little bit. In fact, there's probably more water in this hydro separator than there is in the heat exchanger in this boiler. So I've essentially doubled the volume, the water volume of the water content of this boiler by adding the separator to it and whatever, fluid volume would be in the piping here. So I kind of put a mini buffer tank on this. And you can see here's exactly what I was talking about earlier by putting the supply sensor downstream from the secondary side of the hydraulic separator. When I put my circulator or multiple circulator pumps on this here, I'm going to sense the temperature actually going out to my load, and then this boiler can accommodate that. It can modulate up and down based on what the sensor is telling it. We do make a couple different ways you can put a sensor in there, but that's a little well that we make that goes in there, and that takes what do they call the little 6mm sensors that most of the boilers are coming with those excuse me, small diameter sensors these days. 6mm, about a 1/4 inch diameter. You can put your own well in there. There's, know that is a BSP straight thread. You really should use a BSP fitting in there. You can, with a little bit of Teflon tape on this, make it work. I shouldn't be telling you that. You should really get a BSP to NPT adapter, which you can get from McMaster Carr, and convert that into an NPT thread. This actually is a BSP thread on that little sensor well that we make, but I've seen plenty of guys work around that. We're hoping someday that we can get all those to NPT on our convenience port, I'll call it there. Excuse me. All right, so here's an example of a job, thanks to Corey for sending this in. This is, I just found this on one of the chat rooms and he gave me permission to use it. You can see the value of a hydraulic separator in this. I don't know how he did it, but he got this boiler in this little closet, which is accessed from the outside of this building here. And you can see the separator just saves a lot of space in there. Can you imagine if he had to do a primary, secondary loop and get closely spaced tees for the boiler, closely spaced tees for his distribution, closely spaced tees for his secondary pumps here? That would take up quite a bit of real estate, and that room's got to be 3 feet at the most wide by the looks of the boiler that he's got in there and all the stuff. So a great job, and he made it look nice too of cramming all that stuff in there. It's sometimes you got to do what you do if that's the only space that house had to put a boiler and all that equipment in. The separator can really save you some hassles trying to jam it all in there. I'll just do a couple glamour shots here, and then we'll get on to the video. And I actually have a little tool tech video I want to do too. We got about 10 minutes here. These are just different examples of some of our larger separators. You can see again the relationship of the barrel in the center. Obviously, it's got a little bit of insulation on it to the port coming into it. I like this too, that he made a nice stand for that. He kind of didn't want to hang it off the piping. Obviously, in this case here, you couldn't do that. So it looks like he's just taken some unistrut. He's got some all through there so he can make it leveled up and stuff like that. But that's a nice way to put it in there. And he's put wafer valves on that so he could isolate that if he wanted to, I don't know, work on it someday or drain it down. So thanks for that picture from Comfort Sales, one of our reps here in the Missouri, Illinois area. Yeah, so this example here, now think about this. I've got a lot of pumping stuff going on here, and it's the hydro separator that makes this work. These could all be different size circulators over here. I could have variable speed on one or all of these. These could be variable speed circulators over here. And the key to making all this work and making all these circulators get along with one another, regardless of which one's on, what speed they're running, if they're variable speed, is this one vessel in the center. You got to have that separation of some sort. And they're either closely spaced tees on every one of these, closely spaced tees on this. Throw a separator in there. I've got perfect air removal because I've got my air removal at the very hottest point in my system coming right out of my boiler. I've got my dirt separation at the best spot. I'm going to catch my dirt coming back before it gets into my pumps, before it gets into my system. Got my magnetic function. And there's my expansion tank connection. Everything. It doesn't get any better than that. It's also for a chilled water. We've been talking about heating applications, but we've had quite a few of ours go into chiller applications. So there's just an example of same thing, really, just using blue lines instead of red lines, I guess, to show a chilled water application. And there, again, is an example with a frequency drive, a freak drive on the chillers and distribution circulation there, obviously with chilled water. And this is a clever one. This is actually a job that we did down in Texas, I believe it was. Kevin might remember this, one of our reps down there. And this is what's called hybrid boiler piping. And this actually, there's 5 boilers in this picture. This drawing shows 4, but we had the drawing before the picture was mailed to us. But what they did here is they mixed 2 different types of boilers. So they've got condensing boilers. The first 2 stages here are condensing boilers, and the rest are just conventional boilers. We said, well, why would you do that? And they said, well, why would we buy all expensive condensing boilers if there's a condition when we get up to 140, 160, 180 degree temperature requirement, when these boilers can no longer keep up with the load and the temperature requirement goes up? They said, we might as well be using non-condensing boilers in that case. There's no sense in spending the extra money for a condensing boiler that's never going to condense. So this is what we call hybrid boiler piping, where they mix and match different types of boilers. So the same thing could be going on here. I could have different size boilers. I could have different size pumps. You can see that we put return temperature protection by putting a thermostatic mixing valve on these cast iron boilers. So if they do get a slug of cold water, that valve is going to assure that we don't thermally shock those boilers. And again, there's our point of no pressure change is being established through this header. As long as this header pipe is sized big enough for all the loads connected to it, this becomes the point of no pressure change reference for this pump, for this pump, this pump, and this pump, through the header, through the separator to that pump. So it really frees you up for a lot more creative expansion tank location when you have a separator with all those different options, those 4 ports that you could connect into.
Bob, we've got a question. I'm sorry, on the prior picture.
Okay.
Vince was wondering where the return piping is connected from the loads in this. So not in this installation, but the one prior.
Oh, back one more.
Mm-hmm. Yeah, thank you. Well, let's see. I'm thinking it was that little one, or it could be this one.
Yeah,
Vince,
so
did you want me to? I'm sorry.
Is that the right one?
Yeah, let me, Vince, I'm going to unmute you. Okay,
No,
Vince, if you'd like to.
Yes, in the previous picture, it was the heating diagram he had up.
This
Okay.
one?
Right there, yeah. Where's your return piping coming back from the loads connected?
Right here. So this is going
Right here
out
on the
to my
bottom?
load. Yeah, and these are coming back to my loads. And a great spot, by the way, to put a purge type of valve. I mean, pick a brand. There's a couple of them out there, but Webstone is one of the big ones. So if I put a ball valve there with a purge cock, now I can, purge out every one of these these lines or these loops or these zones, whatever they are, individually. And then once I do that, I can just turn this thing on. There's usually air vents built into the boiler that when I fill them, I'm going to vent air out here, purge out my loops, turn this on, and this thing is going to take off just like that. And you're going to get air and dirt removal through your separator. As any air comes out of solution, as we start heating up these boilers, we're going to get more air out of solution. So this is a really nice way to pipe and to purge those systems. Like putting a purge cock on the individual returns for all those loops. These would want to have check valves, of course, in them, on the distribution side of those circulators. All right, let's get back. Yeah, thank you. So I wanted to kind of set the stage for what you're going to see on the, I wish everybody could be in my shop to show you this, because if you can get really close to this demonstration, it's just incredible how these little micro bubbles come out of solution. We're trying to, get it on film, and sometimes it looks better like a mountain. You take a picture of a mountain, it doesn't look like the same mountain when you're standing in front of it. But we're trying to get a good video here for you folks. But let me explain what's going on. So what I've done here is I've made a clear hydro separator. I've just taken some clear tubing and glued this thing together, put some ports into it. I got 3-to-1 relationship. So what I've got is going around here, I've got a primary loop. We talked about the primary, secondary. So I'm coming down through this, going through this side of the separator is my primary side, going back from the separator, going back up and just making a loop here. Then over here, I put a secondary loop. So I just put a little circulator. I can vary the speed of the circulator here. I've got a flow setter here that I can see what the flow rate's going through there. And I've got a flow setter up on this primary loop, so I can change the flow on these, and you can see the change in the pattern here. So what I did, and this is one of the previous days, I put a different food coloring this. So I'm going to start this up with some red food coloring, and I'm going to run this pump for, I don't know, a couple minutes in the video here. You could run it all day if you want. And you'll see the red food coloring is just going to do this loop right here, and you'll never see any red going over in this side of the loop with the circulator shut off. Then I'm going to shut this off, and I'm going to squirt some blue food coloring in this side, and I'm going to run this circulator without this one running, and this side is going to get, well, I say blue, it's going to turn purple because there's a little bit of red mixed in here. So this is going to go purple, and this is going to stay red. So it gives you a visual that the two flows, even, you know, by changing the pump speeds, I can rev this up, I can rev this one up and down, and you'll see how that separation works. And in addition to that, I'm going to put some dirt in here in this little funnel right here. I'm going to show you how the dirt separates out of there. And I've got a little aquarium pump here. I'm going to pump some air right into this system right here. And I'm going to show you air coming out. I'm going to show you dirt coming out. I'm going to show you magnetic particles coming out. And I'm going to show you the separation function. I think, yeah, so let me see. I got to switch gears here and go to my QuickTime player. And we'll come back. Let me see where I put all that. The other screen. There's my cursor. All right, bear with me, get my player up, turn that on. All right, here we go. It's just a couple minutes long. All right, now it's time for a live demo. Let me kind of set the stage of what you're going to look at here. So we've got a primary loop that goes around, down through this side of the hydraulic separator, through the hydraulic separator, back up just a loop around and around and around. And over here, we're going to call this our secondary loop. And as you can see, I'm just coming out of the top of the hydro separator, going around and back into it. So I'm going to demonstrate 4 different things here. I'm going to show you how hydraulic separation works by injecting a color in here, running this circulator, and you'll see how the flow just goes through this side, shut that off, do an opposite color over here, run that. Also got a low magnet tape down here, so I'm going to show you some magnetic separation. We'll put some magnetic particles in on the top, and while we're running that, we'll let that work, and then we'll blow it out the bottom and see how that works. And you also see air coming out of here, so you can see air, dirt, hydraulic separation, and magnetic particles. So let's go down below and we'll take a look. All right, first I'm going to go up. I'm going to put some metal particles in there. I've got some 409 stainless that's going to stick to this magnet down here as it goes through there. I'm going to dump that in there. I'm also going to pump a bunch of air in it. So you're going to see the air removal and the particle removal first, and then we'll go over and show you how the primary secondary works. So let me quickly dump this in, come back down. See the particles coming down. Air in it. All right, there it comes in. The air coming out here, and you can also see little particles starting to drop down through there. The main thing is how the air is coming out. See the bubbles coming in here that I just pumped in there. The media is collecting it. It's going to come up here, and every now and then you'll see a big gulp come out of the top there. All right, so first I'm going to run the secondary side without running the primary side, and I'm going to inject some red food coloring in here, and you're going to see it just circulate around. You might see a little bit push over here when I first kick the pump on from the force, but you're going to see that red just stay in this loop here when just this pump is running. So let me try this. Going to lose a little water probably doing this. Okay, they're going to start up that circulator. See, almost immediately you can see that red color coming around. Coming into the separator. See it, but it's going right up the side there. Go back up to the top. I've got about 3 gallons a minute going through here. See the red just now starting to come through there as it makes its way up. You can kind of see it migrating up through there. Only got about 3 gallons a minute going through this, so I can have it nice and slow so you can see the air bubbles and everything coming out as we go. So that's this side here, and I could run that for hours, and that red will stay over here. So let me shut this pump off, then I'll go and put some blue in this side. This one off, this one running, and you'll see how the blue, it'll probably turn to purple a little bit. It's going to mix with the red, but that's going to give you an idea how that separation works inside of this chamber. You can see no red coming over here, and the circulator pump's been running now. So turn that one off, and then I go up, put some blue into this side, the primary side, let's call this. Let's see what happens. You ready? All right, put the blue in here. Let's get this pump going here. So I'm going to come down here. Again, I'm going through about, let me see what it is, but it should be about 3 gallons a minute that we're going through there. And now the blue is going to come down. Give it a second here to blend a little bit, get a little bit of air out of there. Okay, the blue's making its way down. Probably could put a little more blue in there. You can see it's starting to come down through the primary secondary pipe. It'll make its way down to the separator. You can see the blue coming down here. Now you can see, obviously it's mixing with the red a little bit. That's why it's turning purple here. So now I've got flow going around through here, through the primary loop. Notice how this is staying red. I'm not getting any purple over here because this is actually separating, even though it's all the same water, all in the same tube. This big chamber in the center becomes my separation device, and that's how I can get the one color going through here, no effect to the color going over here. So next, I'm going to shut it off, and we're going to take the magnet off. We're going to blow it down. I'll show all the particles that we just put in up on top a minute ago and see how the third magnetic separation part of this works. All right, let's put a little bit of particle in there, or put clear water in so you can see this a little bit better. And then we'll go down below and we'll run this for a minute. And let's see, down through the air coming out because I just refilled it. You can see I got my magnet taped on the bottom here. So we're going to give that just a second to run since I just put it in there. Speed it up a little bit. I don't know if you can see the little particles starting to come down here. See them filtering down. I've got some copper in there. I've got some stainless particles. I got some aluminum in there. Got some wood chips, a little bit of everything in there so you can see the different colors coming down. So obviously if you could run this for an hour, we'd get even better result. But let me just shut her off now and blow it down and see what we come up with. So here's the magnet. Let me pull this off and show you what, see what it's collected behind there? Watch when I pull the magnet off. All that stuff just falls right down to the bottom. If I take and blow it down carefully. You can actually put the magnet back on there. Watch this, I'll grab all that stuff from the bottom. See that? There it is, all the stuff that the magnet pulled out of there, the copper and stuff, of course, doesn't stick to the magnet, but that's all the metal particles that I put in there that the little magnet pulled out. The separator does quite a bit of the work. You know, the media in there does the big particles, and the magnet takes those little fine particles out that go through and can stick to the magnet. So there you have it, the demo. Thanks.
And thanks for having a cup of coffee.
Yeah, there you go. All right, now it's time for a live demo. How do I shut this off? All right, I'm gonna get back to my presentation. I'm gonna get my webcam back on. I'll get back in the driver's seat here. Swap displays. All right, I'm back. Well, what do you think?
That was great, Bob. I love it. It was really good visual.
Let me turn my
Had
web.
a lot of other comments here. A lot of people thought it was fantastic. Stephen's wondering if we can get a copy of that video and use it for training. And,
Yeah, no, we don't mind. As long as it's okay with Mary and everybody, I don't mind sharing it. Now, I did one thing, and I hope everybody noticed. I I kind of drained all the color out. It was hard to see the dirt particles with the color, so I did the dirt part of it a second time with clear water in it, because with the purple there, you couldn't see the dirt particles coming down through the separator. And the other thing I realized tonight when I started working, I said, you know what? I had a magnetic band on this separator up here too. So I took that off tonight, and I had some of the magnetic particles I actually caught on the band I had up here. So I actually had two magnetic separators working at one time when I started going through this primary loop. But anyways, I guess the point I would want to make on that is, you know, it's not a battle of how big your magnets is. It's really that media in there that's doing the separation. Most of the work for those particles coming out is because of that collision media, that coalescing media that we put in there that's driving. Again, and if you're standing in front of it, you can just see the tiniest particles come down through that. The magnet just happens to be grabbing the ones that are very fine as they go swimming through the bottom of that. So yeah, I wanted to do one more tech tip, and then I think if you have any questions or anything, this would be it looks like everybody's kind of hanging in there. So I'm gonna show you a little demo here I think might be interesting. Something, another thing that I didn't learn. So what I've got, can you see this, Kevin? Little circulator pump?
Yeah, I can see it. Let me slide my screen here a little bit. I can raise that up. Yeah.
All right. So what I'm going to do is I'm going to plug this little circulator pump in, spin it, and I'm going to show you these little things that are out there. These are called spindicators. See how that little thing spins when the pump is spinning? And they tell you, well, these things will tell you if your pump is running. Let me show you something. The spin indicator spins with the pump not spinning. So if you're going to get one of these and people say it's going to tell you your pump's running, guess what? It doesn't tell you the pump's spinning. It just tells you there's electromotive force there. In fact, you can put one of those spinners on a solenoid valve and it'll spin. And trust me, there's no rotating parts going on inside a solenoid valve. So just a little tip there, when you get those little pump indicators, they don't necessarily tell you that your pump is spinning inside there. They just tell you that pump is powered up. It's more like a voltmeter maybe, or you know, an ammeter or something that's reading the current instead of reading the actual rotation of the pump. So hopefully that's a little tip that you can use if you come across one of those and they're telling you your pump's spinning and you're trying to figure out why you don't have any heat in the house. Could be your pump isn't really spinning. So hopefully, yeah, well, that's what, that's my story and I'm sticking to it. Anything, anything for questions, Mary or Kevin, or?
Let me see. Lots of great comments on the demo. Yeah, that rotating, when I used to sell solenoid valves, you're right, you can put that on a solenoid, it just tells you it's energized.
It just
That
tells
you
you
have the electromagnetic field there. It doesn't tell you that your impeller is spinning or anything like that.
And I see people online all the time saying, oh, I just got this new pump spinner. I can troubleshoot all my pumps and make sure they're spinning when I just walk up to them and put on. And I you know, try and catch them and say, yeah, just be careful with that. It's,
Yeah, so we've had a couple of questions about, actually quite a few about locating the expansion tank. And one says, can it be installed on the supply side of the separator before the secondary circuit? Now, didn't we talk about it's okay to connect an expansion tank anywhere on any of those 4 ports because it's the point of no pressure change, right?
Yeah, exactly. I thought maybe as I went through here, I might find one that's connected on the top on one of these actual jobs. I can't quite see where it is on that one. Yeah, no, any one of the 4 ports would be adequate. Like I say, I like the bottom just because it's in a colder fluid at the bottom than it would be on the, this is probably the best drawing here. It could be here, could be here. Again, I like it down here because the blue line obviously is going to be the colder return water coming back. So your bladder is going to be, or your diaphragm is going to be operating under a little bit cooler temperature here. I think that's the question.
Yeah, that was it. And we get that quite a bit. And there were a couple in here related to that.
Yeah, Kevin also does tech support for us, so he gets a lot of these questions, so he knows the ones that come in over and over again, and maybe we need to put a drawing or something like that in with the box. All right, anything else, or do you want to?
Oh, that looks like about it, Bob. I don't see any questions that we haven't addressed. And by the way, folks, we will answer these if we don't get around to doing it right now. Bob does look at all these later and he follows up on everything.
Yeah, thanks, Kevin, for answering them as we're going here, but I will respond to any questions that came in, and you know, call me at Cluffy.com. You can email bob.rohr@cluffy.com, or you can call up to Cluffy and they can put you through. And if you want to chat about something, I don't mind helping you with whatever projects or questions you might have out there. And if I don't have the answer, I know a lot of people that can help me with getting the right answer to you. So,
well, that's what I do. I call Bob and ask him for the answer, and then it makes me look good.
And then I call somebody else. I mean, we'll call Italy if we have to and ask them, you know, okay, why did you build this like this? And get an explanation in Italian and pass it on to you. But yeah, I appreciate everybody taking time in their evening to come and share an hour or so here with us, and let me know what I can do to help you. And again, thanks to my team. We'll see you next time. Yeah, expansion tanks, that's going to be fun. I put a little time into building this demo that we're going to use next week, and we're going to see if we can maybe get our cameras working a little bit closer, a little bit better too. We think we're getting better with every one of these, but we've got room to improve, so we're going to keep doing it. So
thanks, Bob.
Thanks, Mary. Thanks, Kevin. Thanks, Mechanical Hub, and thanks to everybody that tuned in tonight.